All right, now we're going to get into the limit states associated with compression design, starting with local buckling. We've talked about global buckling, which is when the entire cross section, the entire beam buckles. Now we're talking about individual elements within the cross section buckling. So notice this is something that could also happen in a compression flange of a beam as well. If you have a flange, here we're looking at an I-beam, and we're talking about plate buckling, a buckling of a plate. So if we're looking at a flange and it's subjected to compression, either due to axial compression or eventually due to compression from bending, the flange might have local buckling, right? That's what's meant by local buckling, is an element within the cross section buckles, whereas the global buckling or Euler buckling is the entire beam buckling. Global is the whole thing. Local is just an element within the cross section. Similarly, there is local buckling within the the web. Again, if you have compression, a really slender web plate, you're going to get you might get some kind of local buckling. Hard to sort of see what that would look like, but the plate of the web could buckle. So this is local buckling in the web. So if I want to summarize, there are 4 limit states related to compression. One is called flexural buckling, or this is global buckling of the entire column. Looks like Euler buckling. Then we have local buckling. That is when an element within the cross section, like a flange or a web or a stem, buckles. And then we have torsional buckling. This is when it twists as it buckles. And then you have a combination where you combine these two and you get flexural torsional buckling. I'm gonna provide a video to help visualize these a little bit better. But for now, we're just writing things down. So flexural buckling, torsional buckling, and then combine them and you get flexural torsional buckling. To see what flexural torsional or torsional buckling and flexural torsional buckling looks like, this is torsional buckling. You can see there's a cruciform. Right, if this is your cross section, looking down on it, and it twists while it deforms. Let's see. While it buckles. Kind of looks like a little spider. And then flexural torsional buckling is where not only does it, right, if you think about, if this is looking at an elevation, global buckling is like that. You can kind of see in this, not only is it buckling like that, but it also has a bit of twist to it, right? You can see this has a, torsional has a little bit of twist. Right, there's a displacement and a rotation. This has just the rotation. Torsion, right? Twisting. Flexural torsional has both the Euler buckling, where you have a horizontal displacement, and the twisting of the torsion. If you look at, I thought this might be another way of visualizing it, right? This is, the first one is global buckling, flexural buckling. Let's call it flexural buckling. Called flexural because it is bending, right? Like a beam would, kind of. But the cross section stays the same, it just displaces horizontally. Torsional buckling from the side might not look like too much, but you have this rotation. Right, about this axis. this has a horizontal deflection. Flexural torsional buckling, where we have a displacement as well as a rotation. Right, we still have that displacement and rotation about the longitudinal axis. And then finally, we have local buckling. This is such as in the web. I'm sorry, that's a flange. Such as in the flange, right? Here we have just a little bit of a flange displacement, right? A little bit of buckling in the flange by itself, but the rest of the cross section along the longitudinal axis, you know, remains upright. So another visualization of flexural buckling, torsional buckling, and flexural torsional buckling. Again, kind of look, just another visualization. Flexural buckling, we have our displacement. Torsional buckling, rotation, and then here we have a rotation and some type of displacement. This flexural buckling only makes a bending shape. Torsional buckling just twists, right? And then this one bends, twists, and then bends and twists. Hopefully that's several nice visual examples of these different limit states. These would be global limit states, global meaning the entire member, and then there's the local of the local buckling of an element within the cross section. So local buckling, let's talk about it a little bit more. That is when an element within a cross section buckles due to high compression stress. The likelihood, similar to whether or not something will buckle globally, the likelihood of local buckling is also related to a slenderness ratio. Now we're looking at the slenderness ratio of the element itself. So width, thickness, or your height to thickness. Basically the dimensions of the element as a plate by itself, right? So the width of your flange, well, half the width of your flange, the width of the overhang divided by the thickness or the height of your stem or your web. If your element is stiffened, or the other thing that can help or hurt, or not help, I guess, not hurt, but not help. If your element is stiffened or unstiffened, kind of like this is about related to end conditions, right? We looked at if a column was fixed instead of pinned, it could hold like 4 times the capacity before it would buckle. Why? Because the fixed ends are stiffer, right? They're restraining more movement. Similarly, if a cross-sectional element is stiffened, meaning it's not just flapping out there in the breeze, it's got a web holding onto it or something stiffening it to prevent it from deflecting as much. So let's see, that would be unstiffened. These are the definitions. Unstiffened. The projecting element has a free edge parallel to the compressive force. Stiffened would be the opposite. projecting element is supported along two edges. So unstiffened, there's a free edge parallel to the compressive force. Stiffened, two edges are is supported. Oops, projecting element is supported along two edges in the direction of the compressive force. So let's look at what that would look like. We have some examples. And let's see if they are stiffened or unstiffened. If we first look at the flanges of this WT, right here, would those be stiffened or unstiffened? They are unstiffened, right? They have a free edge. The free edge, if the compressive force is in and out of the page here, then these are our free edges on the sides, right? We'll make them green because they're free, I don't know. Right? Those are free edges parallel to the force, compressive force. Now if I look at this web of this I-beam here, would it be stiffened or unstiffened? All right, it'd be stiffened because these two edges are being held by, supported by the flanges. Two edges supported by flanges. This little chunk of a plate this would be stiffened, right? These two edges are supported by that bolt holding that down. If I'm looking at these little plates right here, right? Probably easy to figure out the pattern. These are unstiffened, kind of flapping out in the breeze. this plate supported by these two I-beams would be stiffened, right? It's got the two edges that are supported by that connection to the I-beams. This little part right here, that would be unstiffened, because again, it's got that free edge way out here. Right, these have the free edges, whereas these have supported edges. And then finally, this little section right here, this would actually be stiffened because they purposefully put that little part down there holding down there to stiffen it, right? That's on purpose. It's to make it stiffer to reduce the likelihood of local buckling. So how do I determine if I have slender elements to see if I need to check for local buckling? I need to check my width to thickness ratio. Going to check the width to thickness ratio of the individual element. And I'm going to compare it to this lambda R. So we can draw better lambda. Lambda R. That's the limiting width to thickness ratio. For a slender element. Basically, if it's less than that, then I don't have to, then there won't be any local buckling. If it's greater than that, then you might have local buckling. So this table right here, table B4.1, is in the spec in chapter B. Table B4.1A, make sure you make it A. It's on page 16.1-17. Make sure it's 1A because that's axial compression. If you flip the page, there is members subject to flexure, and that's not what we're doing right now. Right now we're doing axial compression. So what you'll notice if you look at this table is my lambda r, my limiting thickness ratio is some number, right? This is a number, it's not a hashtag, it's a pound sign, it means number. Square root e over fy, right? Some number times the square root of e over fy, where e, just so we all remember, is 29,000 KSI for steel. So it's also broken down into unstiffened, right? Like the flanges or something, and stiffened. And what do you notice comparing the stiffened versus the unstiffened? The number in front of the stiffened versus the unstiffened. Except for round HSS. Ignore that one. But, right, the number for the stiffened, the number that you're multiplying by that ratio, the number for the ratio of stiffened versus unstiffened, the number for that constant, right? I guess you could use the word constant, right? It's a constant, C. For stiffened versus, or unstiffened, because it's the top one, versus stiffened is less, right? It's usually like 0.56, 0.64. It's actually less than 1, whereas for a stiffened element, it's almost 1.5. Except round HSS, which is its own thing. So that means the number for an unstiffened, the width to thickness ratio for an unstiffened element is less. It means for a stiffened element, you can have a much more slender, right? Your width to thickness ratio can be greater for a stiffened element than for an unstiffened element. Your width to thickness ratio can be greater for a stiffened element before you have to account for local buckling. Which makes sense, right? If it's a stiffened element, similar to if it was a fixed column, it's less likely to buckle at the same compressive force than an unstiffened element or a pin column. So just something to notice. So if you're trying to figure out if you have to account for local buckling, which you don't want to have to account for local buckling, you need to look at the width to thickness ratio and compare it to this limiting width to thickness ratio. In table B4.1a. There will also likely be a note in the dimensions section at the beginning of the manual that says this cross section is shape is slender for compression. Yeah, it'll say something like that. So let's do an example of if local buckling needs to be considered. Let's see, if I look at a W12 by 79, I need to look at both the flange and the web. So if I go back to that table, a flange is an unstiffened element, right? It says flanges of rolled eye-shaped sections. There's also flanges of built-up sections, which we're not going to get into. Rolled is what we're looking at, meaning comes out of the factory that way, as opposed to taking some plates and making your own section. So rolled I-beam, I need to look at my B over T, compare it to 0.56 E over Fy. And now look at that B. That B is actually half of my flange width. So my B over T that I'm looking at is half of my flange width divided by the thickness of my flange. So let's go look at a 12 by 79. Let's see, page 1-26. Half of my flange width is 0.5 times 12.1. My thickness of my flange is 0.735. Gives me about 8.23. Now actually, from here on out, I'm not going to calculate this number. If you look over at 1-27, you'll see a column that's called compact section. Let's see. Criteria. Anyway, W12 by 79, right? But if I look at, can I look at like 2 pages at a time? No, why would I be able to do that? if I look at the opposite page, right, this is where I came up with my thickness of my flange and my width of my flange, which I just got backwards, but that's okay. There's, on the other side, compact section criteria. Right, here is my flange divided by 2, divided by my thickness of my flange. And let's see, 8.22 is the value, which we calculated 8.23. So it's comparable. So let's see, from table, BF over 2 TF is 8.22. So we're going to use those. Now you don't have to even calculate it yourself, right? And let's see, we wanted to compare it to a summer's day. No. 0.56 square root E over Fy. From table 1-1. So lambda R from table B4.1a is 0.56 square root E over Fy. So 0.56 times 29,000 KSI over 50 KSI, right? 8992 seal. You get 13.48 or 49 or something. Doesn't matter. So let's see. My BF over 2TF is 8.22. My lambda is 13.48. My ratio is less, my width to thickness ratio of that flange is less than the limiting width to thickness ratio, therefore flange is not slender. Now I get to check my web. I'm going to look at, right, for my web is stiffened. Webs of doubly symmetric I-beams. You need this H over TW, 1.49. So let's see, my web. H over TW, I can go look it up, right back where I was. H over TW for 12 by 79 should give you 20.7. That's 20.7. By lambda R for a web is 1.49, right? That's what I just saw right back here, 1.49. Times E over Fy, 1.49 times the square root of 29,000 KSI over 50 KSI. Always make sure that needs to be the same units on top and bottom because they're going to cancel out because we're talking about a ratio here. That's why this is the width to thickness ratio is usually inches over inches, so it's unitless, and my lambda is unitless because it's KSI over KSI. So let's see, 1.49. 35.9. So H over TW is 20.7. My lambda R is 35.9. Again, I'm less than it. So my web is not slender either. So I don't need to take into account local buckling. I don't have a slender flange, I don't have a slender web. Okay, what about a 24 by 76? I'm gonna give you guys a couple minutes to do that on your own. And see if you can come up with whether or not you need to account for local buckling. Okay, hopefully you've had a chance to look at it. So let's see if I go to the flange. My BF over to TF is 6.61. My lambda R, because it's the same yield stress and we're still looking at a flange, is still 13.48. You didn't have to recalculate that. So my width to thickness ratio is less, so my flange is not slender. If I look at my web, let's see, my height to my thickness of my web is 49. My lambda R, again, is still 35.9. So, my web is slender in compression. Axial compression. Right, my height to thickness ratio is greater than my limiting thickness ratio. And that probably should have been what we were looking at, a 24 by 76. If we go find a 24 by 76, let's see, 24 by 76. See, there's a little, W24 by 76, there's this little C right here, and it says shape is slender in compression for Fy equals to 50 KSI. That means that one of the cross-sectional elements will fail due to local buckling if you use A992 steel Fy of 50 KSI. So don't select this cross-section if you can help it, right? That's what that means. Let's see if we go back. My lambda R is related to my Fy, so if I decreased my Fy, that would increase my lambda R. I guess that would mean if you decreased your Fy, you would likely fail in global buckling before local buckling. That's probably what's going on. So let's see, I got two more examples. And I'll let you guys try those on your own for a couple minutes, and then so hollow steel section 16, it's a rectangular hollow. And actually it's square. Because it's 16 by 16. Alright, if you haven't finished this example, just pause for a second. But if we go back and look at the table B 4.1, now we're looking at a rectangular HSS, B over T 1.4 times square root E over Fy. So we only have to look at one thing because it's the same thickness and the same dimensions. If it was a rectangular instead of a square, you'd have to look at both B over T's. So let's see, my B over T for a 16 by 16 by 1/2, you should get 31.4. I always like to double check, even though I've done these multiple times, but you know, 16 by 16 by 1/2, B over T equals H over T, because it's a square. Let's see, 31.4. Lambda R is 1.4 times square root E over Fy, which should give you 33.7. So less than the cross section is not slender. And finally, this last example, let's do an angle. If you haven't gotten around to it, press pause and do it yourself. Again, it's equal angle, so L 8 by 8. So this one actually, and maybe it's not quite obvious, but let's see, we go back to our table. You have an angle. Both legs would be unstiffened, right? Because legs of single angles, right? They're both kind of out there. B over T is our width over our thickness. This isn't actually something that we need to look up because it's not in there. B over T. If you look at that table, something like that, make it equal angles here. Those are about the same. We don't have these values at the table. Oh no, what are we gonna do? This is my width. This is my thickness. L 8 by 8. Your width is 8. And your thickness is 1 inch. So my B over T is 8 divided by 1. So that's 8. My lambda R that I need to compare it to is 0.45 E over Fy. And I've now got 36 KSI as my yield stress. So that gives me 12.8, I hope. So B over T compared to my lambda R is less, right? 8 inches. Not 8 inches, 8. And 12.8. So neither leg is slender. I guess, is that symmetric? It's not really symmetric, but equal angle, equal legs. Right, it's 8 and 8. So 6 by 4 would be a different story, but it's not. So that is how you check to see if local buckling needs to be considered. If you find that it does, maybe pick a different section to where it doesn't. If not, you're going to have to account for it in your calculations. We are going to stick to elements, cross sections that we don't have to account for it. At least try to. So that is all for compression theory. Again, we have our 4 limit states of the global buckling limit states, flexural buckling, torsional buckling, and flexural torsional buckling, and then local buckling, which can occur within an individual cross-sectional element. So that is all I have. Thanks.